Welcome to Lecture 6. This week we're going to talk about related rates, linearization and differentials, extreme values of functions on closed intervals, and the mean value theorem. First, let's talk about related rates. The idea here is perhaps we've got two quantities which are connected. And if we change one quantity, then that makes the other quantity change. So the rate of change of one quantity could affect the rate of change of the second quantity. For example, let's suppose we have a spherical balloon. Using the formula for the volume of a sphere, the volume of this balloon, V, is 4/3 pi r cubed. When the volume changes, that means the radius changes, or conversely, if the radius changes, that means the volume changes. How? Well, we differentiate this using the chain rule. dv dt is dv dr dt, or 4 pi r squared dr dt. If we know the radius r, and if we know dv dt, we know how the volume is changing. For example, if we know how much air we're pumping into the balloon, then we can solve this equation and we can find dr dt. We can find the rate of change of the radius. Or another example. Let's suppose we have a water tank which is shaped as a cone with the point downwards. Let's suppose our water tank is 3 meters tall, and let's suppose the biggest radius is 1.5 meters. We're going to be pumping water into this water tank at the rate of 0.25 cubic meters per minute. In other words, 200. So then the question is, if the water is 1.8 meters deep, how fast is the water level rising? We need some variables and we need units. Let t be the time, and we're going to measure that in minutes. Capital V will be the volume of the water in cubic meters. X is going to be the radius of the top of the water at time t, and y is going to be the height of the water at time t. And x and y are going to be measured in meters. And the question tells us that y is 1.8 meters, and the question tells us that dv dt is 0.25 cubic meters per minute. The question asks us to find dy dt. So what can we say? Well, the first thing to note is that 1.5 is a half of 3 meters. And because triangles are similar, because the orange triangle I'm drawing now is similar to the blue triangle, we know that x must be a half of y. So because of the shape of the cone, because the cone is 3 meters tall and has a base radius of 1.5 meters, we know that x must be y over 2. The formula for the volume of a cone is 1/3 pi x squared y, but if x is y over 2, that becomes pi over 12 y cubed. We're going to differentiate this equation with respect to t, and then we're going to find dy dt. So differentiating dv dt is pi over 4y squared multiplied by dy dt. That's the chain rule again. We know that dv dt is 0.25. The question told us that, and the question told us that y is 1.8 meters. So all we need to do is rearrange this equation to find the value of dy dt. And I'll leave it for you to check. Dy dt is approximately 0.098 meters per minute. The water is rising at the approximate rate of 0.098 meters per minute. One slide from the book. This is the strategy your textbook suggests. Your textbook says the first thing to do is to draw a picture. Understand the situation. Decide what variables you want, what constants you have, and I would also add, decide what units you want to use, meters, kilograms, etc. What do you want to use? Step 2, write down the numerical information that you know. What does the question tell you that you know? Step 3, write down what you're asked to find. In the last example, we were asked to find dy dt. Step 4, get an equation which relates the variables, and then step 5, differentiate it. And then finally, step 6, rearrange your equation to get what you want. Evaluate the thing that you're asked to find. So for example, let's look at example 2 from your textbook. A hot air balloon is rising straight up from a level field, and this is tracked by a rangefinder 150 meters from the liftoff point. At the moment, the rangefinder's elevation angle is pi over 4. The angle is increasing at the rate of 0.14 radians per minute. How fast is the balloon rising at that moment? So let's draw the picture. We have it at the top. We have a triangle, 150 meters at the bottom. We have an angle theta, and we're told that when theta is pi over 4, d theta dt is 0.14. That's what the question tells us. And the question's asking us to find dy dt when theta is pi over 4. Let's go through the steps in this order that the book suggests. Step 1, draw the picture. Here it is. Name the variables and the constants. Theta is going to be the angle in this picture, and it's going to be measured in radians. Y is going to be the height of the balloon above the ground, and that's going to be measured in meters. T is going to be time, and for time we're going to use minutes. Step 2, what do we know? The question tells us that d theta dt is 0.14 radians per minute when theta is pi over 4. Step 3, what do we want? We want to find dy dt when theta is pi over 4. Step 4, write an equation which relates y and theta. Well, we just have a triangle here. Here's the angle theta, and here's y, and the base is 150. So y must be 150 tan theta. Step 5, differentiate with respect to t using the chain rule. The derivative of y is just dy dt. The derivative of tan theta is sec squared theta d theta dt. And then step 6, get the answer that you want. We're going to put in theta is pi over 4, and we're going to put in d theta dt is 0.14, and we'll find that the answer that we want is 42. That means the answer to this question is 42 meters per minute. Now, your textbook has lots of examples like this, and the idea is all the same. Drawing a picture, write down what you know, write down what you want, write down an equation, differentiate it with respect to the chain rule, and then get the answer that you want. I'm going to leave these for you to read. I don't think it's worth my time repeating the same idea again and again and again. So I'll leave examples 3, 4, 5, and 6 in your textbook for you to read. I want to move straight on to linearization and differentials. Two different ideas in one section. To start with, let's look at the graph y is equal to x squared, and I'm interested in the tangent line to the graph of y is equal to x squared at the point 1, 1. And I want to zoom in on the point 1, 1. Here we go, and then let's zoom in again. Zoom in again. Zoom in again. Zoom in one more time. We can see that if x is close to 1, then x squared is approximately equal to its tangent line, which is 2x minus 1. That's the idea in this section. If a function f is differentiable at x is equal to a, then the approximating function, that's another way of saying the tangent line, is capital L of x equal to f of a plus f prime at a, x minus a. This is called the linearization of f at a. And this is useful because if x is close to a, then our function f of x is approximately equal to its linearization. This is called the standard linear approximation of f at a. The point x equals a is called the center of the approximation. So, for example, find the linearization of f of x is equal to the square root of 1 plus x at x equal to 0. And because your textbook is an American book, they like to spell linearization with a Z. So we're going to be doing this pink line just here. The tangent line to our blue curve when x is equal to 0. And if we zoom in on this small green box, we get this picture. So, first thing we do is we differentiate our function. We get a half 1 plus x to the power minus a half. And then we put in x equal to 0 to get a half here. We also want f at 0 because we're doing the approximation centered at 0, and f of 0 is equal to 1. So if a is equal to 0, the standard linear approximation f of a plus f prime at a x minus a becomes 1 plus a half x minus 0, or just 1 plus x over 2. Now, how good an approximation is this? Well, let's suppose we're looking at x is 0.05. If we use the approximation, we would calculate 1.00250, or if we calculated the exact value, we would get approximately 1.002497. That's pretty close. The error, the difference between the true value and the approximation, is less than 10 to the power minus 5. Or if we zoomed out a little bit and we looked at, say, 0.05, the true value is 1.024695, and our approximation gives us 1.025. Still quite a good approximation. The difference between them, the error, is less than 10 to the power minus 3. Another example, find the linearization of the same function, square root of 1 plus x, but this time at x equal to 3. So we're going to do the same thing, but this time with a equal to 3. So we need f at 3 and we need f prime at 3. And then we put these into the formula for L, and we find our linearization, or our tangent line, is 5/4 plus x/4. So for example, if we're looking at x equal to 3.2, our approximation gives approximately 5/4 plus 3.2/4, which is 2.050. And that's pretty close to the true value, because the true value, square root of 4.2, square root of 1 plus 3.2, is actually 2.04934. So the difference is less than 1,000th. Find that linearization of f of x is equal to cos x at x is equal to pi/2. We're starting with this blue graph, and we want to find the equation for the pink line. We want to find the tangent line to our graph when x is equal to pi/2. So what do we need? We need our value of our function at a, so f at pi/2, and we need f prime at pi/2. And then we put them into the standard equation. The standard equation for a linearization, or for a tangent line, is f of a plus f prime at a, x minus a. F at a, or f at pi/2, is 0. F prime at a, that's f prime at pi/2, is minus 1. Put these in and simplify. The tangent line is y is equal to minus x plus pi/2. The linearization is minus x plus pi/2. Now let's look at the function f of x is equal to 1 plus x to the power k. And we're interested in this close to x equal to 0. So we're looking for a linearization centered at x equal to 0. The linearization is going to be f at 0 plus f prime at 0, x minus 0. And because if we differentiate f and then put x equal to 0, we get f prime of 0 is equal to k. And if we just put 0 into f, we get 1. So the linearization is 1 plus kx. I'm going to put this equation in the yellow box at the top. Here we are. The approximation is 1 plus x to the power k is approximately equal to 1 plus kx, as long as x is close to 0. So, for example, the square root of 1 plus x, that's 1 plus x to the power of a half, is approximately equal to 1 plus a half x. Second line, 1 over 1 minus x, or 1 plus minus x to the power minus 1. Now that sort of looks like what we have at the top. We have k of minus 1, but there is a difference here because instead of plus x, we have plus minus x. But that's okay. We'll still use the same formula, but instead of x, we're going to be writing minus x. So it's 1 plus k, that's 1 plus minus 1, multiplied by, instead of x, we have minus x. So 1 plus minus 1 multiplied by minus x, which is 1 plus x. As long as x is close to 0, 1 over 1 minus x is approximately equal to 1 plus x. What about the third one? Here I have 1 plus 5x to the power 4 to the power a third. So k is going to be a third. It's going to be 1 plus k something. So 1 plus a third and then the something. And what is the something? Instead of x, I actually have 5x to the power 4 here. So the something is going to be 5x to the power 4. Simplify that, 1 plus 5 over 3, x to the power 4. And then finally, the last one, the idea is the same. 1 over the square root of 1 minus x squared, that's the same as 1 minus x squared to the power minus a half. Here, k is equal to minus a half, so we can write that in. 1 plus k multiplied by the something. What is the something? The something is minus x squared. And we can simplify that to 1 plus a half x squared. So that's linearization. The second half of this section is about differentials. We've been writing dy dx for the derivative of y. Now, this doesn't mean dy divided by dx. This notation means the derivative of y with respect to x. But what if we did want it to mean dy dx? How could we do that? What we could do is we could create two new variables, two new things called dy and dx, and we want to create them such that dy divided by dx is equal to the derivative of y. So we do it like this. Let's suppose y is equal to f of x is a differentiable function. Our first thing, the differential dx, is just going to be an independent variable. Something that we don't have control over. It's just some variable. It could be anything. And then after that, we're going to define the differential dy using this formula. dy is going to be f prime at x multiplied by dx. And why are we doing this? We're doing this so that dy divided by dx, that's f prime at x dx over dx. The dx is cancelled, and that's just f prime at x or dy dx. So if we define dy using this formula, then it means that dy divided by dx is the same as dy dx. And that's going to be useful when we get to mathematics 4, we start solving differential equations. For example, find dy if y is x to the power 5 plus 37x. And part B, Find the value of dy when x is equal to 1 and dx is equal to 0.2. So we go back. Here's the formula. dy is the derivative of our function, and then we just multiply it by dx. So we're just going to take our function, we're going to differentiate it, and then we're going to multiply it by dx. dy is the derivative of the function. Derivative of x to the power 5 is 5x to the power 4, and the derivative of 37x is 37, and then we just multiply it by dx. That's all we do for differentials. We're just doing a normal derivative, and then we're multiplying it by dx. And then part B, we're asked to find the value of dy. So we put x equal to 1 in, and we put dy equal to 0.2 in. Here's x equal to 1, and here's dx is equal to 0.2. And then we can calculate that that's 8.4. Another one, if f of x is 3x squared minus 6, then the differential of f, that's d of f, or d of 3x squared minus 6. What's the derivative of 3x squared minus 6? This derivative is just 6x, and then we multiply it by dx. That's all we're doing when we're doing differentials. We're just doing all the derivatives that we know how to do, and then we multiply it by dx. And it doesn't get any more difficult than that, because all the formulas that we're used to, like for example, the sum rule, d dx of u plus v is du dx plus dv dx. We just have a corresponding formula for differentials. D of u plus v is d of u plus d of v. Or we know that the derivative of sine u with respect to x is cos u du dx by the chain rule. We can do the same thing for differentials. D of sine u is cos u du. Let's think about this another way. Think about the differential formula that you know, and then just cross off the dx's on the bottom. D of sine u is cos u du, and it's that easy. For example, we can use the chain rule and the other differential rules to find differentials of functions. D of tan 2x, derivative of tan is sec squared, so we have sec squared 2x multiplied by d of 2x. And d of 2x is just 2 dx. So that's 2 sec squared 2x multiplied by dx. Or in B, it's a quotient rule question. D of x over x plus 1. Differentiate the function on the top, or in other words, do d of the function on top, and then multiply it by the function on the bottom. And then minus, keep the function on the top as it is, so just x, and then do d of the function on the bottom, and then divide by x plus 1 squared. Now we can simplify this a little bit, because sum rule, d of x plus 1 is the same as d of x plus d of 1. But d of 1, derivative of 1, is just 0. So that's just d of x. We get x dx plus dx minus x dx on the top, which is just dx. Let's talk briefly about estimating with differentials. And this is going back to a similar idea that we were talking about when we were talking about linearization. Let's suppose we have some complicated function, drawn in blue here, and we want to estimate it using the tangent line. Suppose we know that a value of f of x at x equal to a, and we want to estimate how much this value will change if x moves to a plus dx. Well, we can see from the picture how much it really changes. It really changes this much. And we can see how much the approximation changes. The approximation changes this much, which is the same as dy. So we can see that if dx is small, then these two things are going to be roughly the same. This distance will be roughly the same as this distance. Or that's the same as saying f at a plus dx, which is what we want, is approximately equal to f at a plus dy. How can we use that? For example, use differentials to estimate 7.97 to the power a third. We can think of using linearization around the center 8, because 7.97 is approximately 8. So note first that if y is equal to f of x is equal to x to the power a third, then dy is 1 over 3 x to the power 2 over 3 dx. Because dy is just f prime x dx. So because we're close to 8, actually 7.97, the number we want, is 8 minus 0.03. We're going to be using dx is minus 0.03. That's how much the x is going to change. We want to calculate f at 7.97 because we want to calculate 7.97 to the power of a third. So in other words, we want to calculate f at a plus dx. We want to calculate f at 8 minus 0.03. And that's approximately equal to f at a plus dy. F of a is easy. 8 to the power of a third is just 2. And what is dy? We know that as 1 over 3x to the power of 2 thirds dx. So 1 over 3, 8 to the power of 2 thirds, multiplied by minus 0.03. What's 8 to the power of 2 over 3? Think about it like this. That's 8 to the power of a third, and then squared. But 8 to the power of a third, or cubed root of 8, is just 2. So that's just 2 squared, or 4. So we can calculate that 7.97 to the power of a third is approximately equal to 1.9975. The true value is actually 1.9974968684, etc., etc. So we're pretty close. We've done an easy calculation and we found the approximate value of it without doing any complicated calculations, without you having to use a calculator. And for a lot of purposes, this would be good enough. Let's do another example. Let's suppose we have a circle. Here we are. And let's suppose the radius of our circle is 10 meters, but then we increase it to 10.1 meters. Estimate the increase in the area of the circle. Estimate the area of the enlarged circle and then compare your estimate to the true area. Area of a circle, pi r squared, we know this. Differentiate it, dA, how much the area is going to increase, 2 pi a dr. A, the radius of the circle is 10. How much are we increasing the radius? We're increasing it by 0.1. So we're increasing by 2 pi meters per second, approximately. So that means the area of the new circle, the bigger circle, is approximately the area of the circle we started with plus 2 pi. So approximately 102 pi. So just doing this simple calculation, we can say the area of a circle of radius 10.1 meters is approximately 102 pi meters squared. What's the real area of this triangle? Of this circle? The real area of the circle is actually 102.01 pi meters squared. So we're pretty close. We have an error of 0.01 pi. Let's talk a little bit about the error here. The error if we do a differential approximation. How well does f of a plus dy approximate f of a plus dx? Well, we can see from this picture that the true change, how much does the function really change as we move from a to a plus dx, is this. It's f of a plus dx minus f of a. And what is the approximate change? The approximate change, this distance. F prime at a dx is how much the linearization changes as we go from a to a plus dx. And the error is going to be the difference between these two. So that's f at a plus dx minus f at a minus the approximate change f prime at a dx. And I'm going to write that like this. I want to write that as everything multiplied by dx. So I want to write that as f at a plus dx minus f at a over dx. That should look familiar to you. And then minus f prime at a dx, or some number epsilon dx. So the true change is going to be dy, the differential f prime at a dx, plus this error number multiplied by dx, plus the error. In example 6, that was the one with the circles, going from a circle of radius 10 meters going to a circle of radius 10.1 meters. The real change in area, we can write like this. It's the 2 pi that we found was the approximate change plus the error. And that's all I want to say about differentials. We're going to take a break now, and then I'm going to continue at 3 o'clock when I start talking about chapter 4. And let's continue. Section 4.1 is about extreme values of functions on continuous intervals. Look at the graph of this function. Where is the function biggest and where is the function smallest? And what is the biggest or the maximum value of this function? We can see that the function is biggest just here. The value of the function here is called the absolute maximum value. And where is the function smallest? The function smallest just here. The function is smallest and it has a value equal to the absolute minimum value just here. Let's talk about the biggest point first. It's biggest when x is equal to c. And we know it's biggest because f at c is greater than or equal to f at x for any x. Before I go on, let me just explain how the plurals. We know that in English, the usual way is we put an s on the end of a word, but that's not always true. The plural of man is men, and the plural of extremum is extrema. So the same for maximum and maxima, minimum and minima. Definition. Let's suppose f is a function with domain capital D. Function f has absolute maximum value on its domain D at a point C if f of x is always less than or equal to f of c for all x in the domain D. And we have the same idea for minimum. The only difference is that for minimum, we changed the inequality around. F has an absolute minimum value on D at a point C if f of x is greater than or equal to f of c for all x in the domain D. Maximum and minimum values are called extrema or extreme values. For example, let's look at the function y is equal to x squared on some different domains. First of all, let's suppose the domain is the whole real line. That's the open interval from minus infinity to infinity. And I've drawn its graph. This function does not have an absolute maximum because it's going up and up and up and up all of the way to infinity. But it does have an absolute minimum value of 0, and this occurs when x is equal to 0. What about if we restrict the domain to the closed interval from 0 to 2? Here's the graph. We can see that now we have an absolute maximum value, which is equal to 4, and that occurs when x is equal to 2. And we still have the same absolute minimum value of 0, which occurs when x is equal to 0. The half open interval between 0 and 2 next. Here's the graph. Now we have an open circle at 0 because x equal to 0 is not in the domain of the function. The absolute maximum value is 4, and that occurs when x is equal to 2. This function does not have an absolute minimum value. Remember, 0 is not in the domain. There is no point in the domain where the function is smaller than every other point in the domain. So there's no absolute minimum. And then finally, if we have the open interval between 0 and 2, then this function does not have an absolute maximum value and it does not have an absolute minimum value. There are no absolute extrema for this function. The extreme value theorem. You know a theorem is going to be an important theorem if it has a name. Suppose that f is a continuous function with domain D, and let's suppose that the domain of this function is a closed interval. then f attains both its absolute maximum value and an absolute minimum value on this closed interval. So let's go back to the previous one. The theorem says if the domain is a closed interval, then we always have an absolute maximum value and we have an absolute minimum value. Now, what does this say? The extreme value theorem says there's numbers x1 and x2 in the domain, that's the closed interval from a to b, such that f of x is small m, f of x2 is capital M, and f of x is always between small n and capital M for all values of x in the domain. So what could that look like? Our function might look something like this. We could have the absolute maximum and the absolute minimum at interior points. So not at the end points of our closed interval, but somewhere in the interior. But that's not the only possibility. We might have a function like this. This function has absolute maximum and absolute minimum at the end points of the domain. Or maybe we have a function like this. Here the absolute maximum is at an interior point, but the absolute minimum is at an end point. Or turn that picture upside down, something like this. This function has the absolute maximum at the end point of the domain and the absolute minimum at the interior point. Those are the possibilities. The maximum and the minimum, they're either going to be at the left end or the right end, or they're going to be somewhere in the middle. But as long as the domain of our function is a closed interval, we know that the function must have an absolute maximum and it must have an absolute minimum. There's more extreme values that we can talk about. We can talk about local extreme values. First, let's talk about this one just here, this local maximum. The idea is, what do we get if we look close to C? Let's suppose we just look at the function between these two orange lines. So forget about the rest of the function. Cross it all off. If we only look close to the point C, then we can see that we have a maximum. We have the biggest point on the graph. If that's true, then we say we have a local maximum. Likewise, this one is a local minimum, because if we only look close to here, then we have a minimum. F at this point is smaller than f of x for all x close to it. An absolute maximum is also always a local maximum, and an absolute minimum is also a local minimum, but the opposite is not, converse is not true. This point is a local maximum, but it's not an absolute maximum because the function is bigger somewhere else. Here's the definition. A function f with domain D has a local maximum value at a point C in its domain if and only if f of x is less than or equal to f of c. Same so far, but instead of saying for all x, we say for all x close to C. And then almost exactly the same, but just changing inequality. F has a local minimum value at a point C if f of x is greater than or equal to f of c for all x close to x. As I said on the previous slide, an absolute maximum is always a local maximum too, and an absolute minimum is always a local minimum too. Another theorem with a name, so another one that's going to be an important one. This theorem is called the first derivative test for local extrema. Suppose that f has a local maximum or a local minimum value at an interior point. So not at the end point, it's somewhere in the middle, an interior point. And let's suppose that f prime at C exists, f prime at the interior point where the local extreme maximum is. Then the theorem says the derivative of f at c must be 0. If we're at a local maximum, the derivative, if it exists, must be 0. If we're a local minimum, the derivative, if it exists, must also be 0. So what does that tell us? That tells us that there's only 3 types of places where we can have an extreme value. We could have an extreme value at an interior point where the derivative is equal to 0. Or we could have an extreme value at an interior point where the derivative does not exist. Or the third possibility is we could have an extreme value at endpoints of our domain D. The first 2 are interesting to us. We give these a name. These are called critical points. An interior point of D where either the derivative is equal to 0 or the derivative does not exist is called a critical point of f. So now we have a strategy for how to find the absolute extrema of a continuous function defined on a closed interval. Step 1, find the critical points. Find the interior points where either the derivative does not exist or the derivative is equal to 0. Step 2, we're going to calculate the value of our function at all of the critical points. Step 3, we're going to calculate f at the end points. And then step 4, we're going to take the largest and the smallest values from this list. The extreme value, so the first derivative test tells us that the extreme values are either at critical points or they're at end points. So we don't need to look anywhere else. We don't need to look at the rest of the domain. We only need to look at the critical points and at the end points. So, for example, find the absolute maximum and absolute minimum values of f of x is equal to x squared on the closed interval from -2 to 1. Step 1 is to find the critical points. Critical points means either the derivative does not exist or the derivative is equal to 0. But this function is differentiable on the whole of its domain. So there are no points where the derivative does not exist. So that means the only critical points we can find is where the derivative is equal to 0. So we start by looking at f prime of x is equal to 0. And for this function, f prime of x is 2x. So that means the only critical point of this function in this domain is x equal to 0. Step 2 is calculate the value of the function at every critical point. F of 0 is equal to 0. Step 3, calculate the value of the function at the end points. The end points are -2 and 1. So we calculate f of -2 is 4, and we calculate f of 1 is 1. We've got 3 numbers here, 4, 1, and 0. Which one of these numbers is the biggest, and which one of these numbers is the smallest? The largest and smallest numbers are 4 and 0, of course. So that means the absolute maximum value of this function is 4, and the absolute minimum value of this function is 0. Let's do another example. Find the absolute maximum and absolute minimum values of 8t minus t to the power 4 on the same closed interval from -2 to 1. And the technique is the same. First, we'll find the critical points. Step 2, we'll calculate the value of the function, all of the critical points. Step 3, we'll calculate the value of the function at the endpoints. And then step 4, we'll choose the biggest number and the smallest number. The first thing to note is G prime exists for all of the interior points. We don't have any points where G prime doesn't exist. So instead, we only look for the points where G prime is equal to 0. Starting with 0 is equal to G prime of t, which is 8 minus 4t cubed, rearranging that, and we get t is equal to the cubed root of 2. But the cubed root of 2 is bigger than 1. That means that the cubed root of 2 is not in our domain. So we can forget about that. We don't need it. So in the closed interval from -2 to 1, there's no points where G prime does not exist, and there's no points where G prime is equal to 0. G does not have any critical points between -2 and 1. Step 2, calculate the value of our function at all of the critical points. We don't have any critical points, so there's nothing to do. So let's move on. Step 3, calculate the value of G at the endpoints. G at -2 is -32. G at 1 is equal to 7. And then finally, step 4 is choose the biggest number and the smallest number. We've only got two numbers. We only have -32 and 7. So clearly the biggest number here is 7 and the smallest number is -32. So the answer to this question is the maximum of G on the closed interval from -2 to 1 is 7, and the minimum of G between -2 and 1 is -32. And if I show you the graph of this function, remember we're only looking between -2 and 1. We can see from the graph the maximum is 7 and the minimum is -32. Find the absolute maximum, absolute minimum values of h of x is equal to x to the power 2/3 on the closed interval from -2 to 3. Step 1, let's look for critical points. So to start with, by differentiating x, and we get the formula 2/3 cubed root of x. So what can we say here? We can say that h prime does not exist if x is equal to 0. And we could also say that h prime is always not equal to 0 on the rest of the domain. So there's one point where h prime does not exist, and there are no points where h prime is equal to 0. For this example, the only critical point is x equal to 0. Step 2, calculate h at every critical point. H of 0 is 0. That was easy. Step 3, calculate the value of h at the end points. H at -2 is cubed root of 4, and h of 3 is cubed root of 9. So what do we have? We have three numbers. We have the number 0, we have the number cubed root of 4, and we have the number cubed root of 9. Which of these three numbers is the biggest? Which number is the smallest? So step 4, we choose the biggest one for the maximum. The maximum of h is cubed root of 9, and the minimum of h must be 0. Let's repeat this example. Step 1 is to find the critical points. So we either want to find all of the points where h prime is equal to 0, or we want to find all of the points where h prime of x does not exist. This is what we want. The first thing I'm going to do is I'm going to differentiate h to get a formula. H prime is 2 over 3 cubed root of x. When does this not exist? It doesn't exist when x is equal to 0, because then we would be doing 2 divided by 0. So we can say that h prime does not exist if x is equal to 0. So 0 is a critical point. The second type of critical point is the critical point where h prime is equal to 0. But we can't solve this. We can't solve 2 over 3 cubed root of x is equal to 0 if x is not 0. So that means there's one critical point. At 0, h prime does not exist, and there are no points where h prime is equal to 0. So there's one point where h prime does not exist, and there are 0 points where h prime is equal to 0. There's only one critical point. The only critical point is x is equal to 0. Calculate h at 0, calculate h at the endpoints, and then take the biggest number and the smallest number. Out of 0, cubed root of 4 and cubed root of 9, the biggest number is cubed root of 9, and the smallest number is 0. And the graph of the function looks like this, and we can see that this is true. We can see that because we have a corner here, we can see that the derivative does not exist at 0, and we can see that there's no points where the derivative is equal to 0. We can see that we have an absolute minimum when x is 0. We have an absolute maximum when x is equal to 3, and we have a local maximum when x is equal to -2. Our final section for today's class is the mean value theorem. But before we can talk about that, we need to talk about another theorem called Frollic's theorem. Let's suppose that we have a continuous function which is defined on a closed interval from a to b. Let's suppose that our function is differentiable on the open interval from a to b, and let's suppose that f of a is equal to f of b. So we have a function which looks something like this. It might not look exactly like this. It might wiggle up and down, whichever way you want it to, but we need it to be differentiable, we need it to be continuous, and we need f of a to be equal to f of b. Then Rolle's theorem says there exists a point C in the open interval from a to b, so there exists a point C between a and b, such that f prime of c is equal to 0. Now, in this picture, the graph goes up and then it goes down. Somewhere in the middle, there must be a point where the graph is horizontal, a point where the slope is equal to 0. Or if we look at the second picture here, the graph goes up, down, up, down. This one actually has 3 points where the slope is equal to 0. Rayleigh's theorem says there exists at least one point somewhere between them where the slope is equal to 0. The mean value theorem is a more advanced version of Rayleigh's theorem. We start with the same first two hypotheses. Again, we want a function which is continuous on a closed interval and differentiable on the open interval. Then the conclusion is there exists some point C between A and B such that f of b minus f of a divided by b minus a is equal to f prime c. What does that mean? Let me show you a graph. The dashed line in this graph is y is equal to f of a plus f of b minus f of a over b minus a, x minus a. And the slope of this dashed line is f of b minus f of a divided by b minus a. The mean value theorem says somewhere between a and b, the graph will have the same slope as the dashed line. And we can use that for things like this. Use the mean value theorem to show that the function x squared has a point where its derivative is equal to 2. Now, we have a function which is continuous on the closed interval from 0 to 2. It's differentiable on the open interval from 0 to 2. F of 0 is 0 and f of 2 is 4. By the mean value theorem, somewhere between 0 and 2, there's a point C where f prime of c is equal to f of 2 minus f0 over 2 minus 0. And because I've chosen 0 and 2 carefully, this is equal to 2. And I'm going to finish by talking about two consequences of the mean value theorem. First, corollary. Corollary is like a small theorem which comes after a big theorem. So corollary or small theorem. If f prime of x is equal to 0 at each point between a and b, then we know that f of x is equal to a constant for all x between a and b. And the second corollary, or second small theorem which comes after a big theorem, if we know that two functions have the same derivative at each point between a and b, then we know that f of x must be g of x plus a constant for all x between a and b. And these are going to be important ideas when we start talking about integration. Let me go back to the previous slide. Question in the chat, how do we know that it's continuous between 0 and 2? Because it's a polynomial. And as we saw earlier, all polynomials are continuous everywhere. And that is the end of today's lesson. Next week, we're going to finish chapter 4. That will be the end of our discussion of differentiation. We'll talk about monatomic functions and the first derivative test, concavity and curve sketching, applied optimization, and antiderivatives. Are there any questions? I don't have the 2022 papers because in 2022 the exams were online exams and they weren't the same type of exam. They were, I don't know what type of exam. I don't know if they were multiple choice or what, but I think they're not relevant for you because they were a completely different type of exam.